Hello and welcome to this video which will be demonstrating Instinct AI, which is a behavior tree library for Unity. This here on the screen is a preview of what we will be building in this video, or part of it. This is a behavior tree, and if you're not familiar with behavior trees, they are a way of expressing behaviors of characters in games or whatever in a kind of intuitive hierarchical manner, a tree, and there's a whole bunch of different nodes with different functionality that you can use to build up these behaviors and to select different behaviors based on different inputs and kind of respond to the environment within the game. So I will get rid of this for now and go back to this project, which is basically a blank slate. So we have an arena, as I've called it, which is just a plane in space. Now if we look at the game view here, we can see it's just a big blue space, and this is where we'll place our characters and build up their behaviors. What we're going to be doing is we've got a cat and we've got a mouse and we've got some cheese. The mouse is trying to eat the cheese so he doesn't starve, and he's going to be interacting with the cat and the cat with him. So if we go over to this tab here, we see we already have Instinct AI installed. This is a beta release, so this is a pre-release of the asset. It's functionally complete, but it still has a couple of rough edges that need tidied up before it gets a full release. But it's good enough to kind of demonstrate it at the moment. As you can see in the hierarchy view, if we go back to the scene, we have a camera and we have this big blue plane and there's nothing else. In the project view we have a bunch of sprites. We have an empty script folder. We have a prefab, which is a piece of cheese. We just drop that in. If we click on it, you can see it's just a simple sprite, nothing else. We have Instinct AI, materials, gizmos, and that's it. There's nothing else. So, with Instinct AI, the big difference between it and other libraries that you may have used to express behavior trees in the past is that it is very code oriented. There is essentially zero runtime code with the library. So when you're building up trees that express behaviors, you're actually building them up in code using a code generator. And these just become simple mono behaviors which you attach to your scripts in the normal way. I think the easiest way to show this is to just do a simple example. So if we now go to our scripts folder, as I said, it's a code generator, so the behavior trees that you create correctly belong in the scripts folder. So we're going to create one now. Create a behavior. I'm going to create one for the arena itself, and what you can see is that as soon as you create a behavior tree, we'll just double click on it. So we've got our empty behavior tree here. You also get two extra files, C# files, which are the mono behavior class. So if we open one of these up, in Visual Studio, you see that it is a regular empty class, which derives from mono behavior. And if we give Visual Studio some time to load, it seems to be taking its time loading this project. There we go. We can see that there's a second file, which is the generated file. So you'll notice this partial keyword here. Partial classes, if you're not familiar with them in C#, allow you to declare a class and spread its functionality across multiple files. So in our case, we've got the generated portion, which contains everything that describes the behavior tree, and the user portion. So this is the part of the class which is safe for you to edit, so you can add your own functionality to them, just like a regular Warner behavior. And whenever you change the tree, Instinct AI will regenerate this part, and it won't interfere with this part. And the compiler will see it as one class. So it's basically a neat way to kind of compartmentalize generated portion and the user portion of a class, of a behavior tree class. So if we go back in here, we can start to build up a tree. So we have a whole bunch of different types of nodes, and we're going to start with a sequencer. So a linear sequence. This little marker here is your start node. So anything which links back to the start node becomes part of the tree. So if we drag this back here, we start a sequence. And then we're going to add in two little actions. We're going to add a wait node and a custom action. We're just going to link these in. So in fact, what I'm going to do is I'm going to reorder these, swap them over. So what this tree does is basically runs these two nodes in sequence. It will call some custom action, which we will define in a moment. Then it will wait for some specified period of time, and then it will just repeat over and over again. So what I want to do first of all, before I forget, is I'm going to change this wait period to something random. So it's going to wait between 0.1 seconds and 10 seconds. And the action, at the moment it says no op, so it's not set to do anything. We want this to be a method call, but we don't actually have any methods yet that it can call. And what this tree is actually going to be doing, it's going to be spawning cheese everywhere. So let's add in a method. Move over to our arena class. And this is the simplest custom behavior you can have. So every custom behavior has to return this node val type, which basically tells the behavior tree at what state is this action currently at. So the possible values are success, which means it's done, you can move on to the next node, or running, or fail. There's also error or invalid, but you tend not to need to use those. So fail means that, for example, you failed to spawn the cheese, it didn't work for some reason. And success means we have spawned the cheese, so we will definitely spawn some cheese. In fact, what we will do is add in a reference to the prefab so that we can actually spawn something. And we will also have a list of all the cheese that we have spawned. Let's make that a simple list. Oops. There we go. So we now have a list of cheeses that we have spawned, and we can add to that list. So first of all, let's just go back here and see how you would wire this up. The arena in the hierarchy view is now acquired. Oh, we haven't added the component. So we can just drag the component onto the inspector or to the object in the scene view just as you would normally. It's just a regular mono behavior. It just happens to be generated by this editor. And you can see down at the bottom of the editor here, it shows you which class you're editing. And we can choose the cheese prefab for it to spawn into the scene. So there we go. And the thing to note about this, well, first of all, we've not quite finished. Let's just do method call. And you'll see it's automatically selected spawn cheese as the method call because it's the only method available. The method itself could be in a base class, or it could actually be in a component. If you have another component on your game object, and that component is known to the behavior tree library, you can configure it. I'll show that later. Then those methods will be added in here as well. So now that we have this method in here, this tree is essentially doing exactly what we want it to do. And all we have to do is hit this regenerate code. This button turns green once the code is up to date and matches the tree. Back into Visual Studio, and we can see the generated class has been updated with a whole bunch of code that does what we want it to. So let's spawn some cheese. Okay, well, first of all, we kind of want to spawn, we have this kind of blue area, so what we want is the cheese to spawn somewhere in this blue area. And since this is a super simple example, we're going to hack this in as the bounds of the big blue plane. So let's just, let's put it in the right method first of all. Let's get the renderer so that we can find the bounds. And then we'll work out the rectangle from the bounds. Just fill these in a moment. Create a field for that. Now, what have I done wrong here? What is it telling us? Oh, because I didn't actually get the bounds, did I? There we go. There's probably a better way to do this, but I'm just hacking this in just now just to get something working. The extents of the rectangle is half of its width, which is why we're multiplying by 2. In fact, since the cheese center point is, well, it's in its center, let's just add in a bit of border just to make it a bit neater. Create a wee constant for that. And then we can do the same down here. Oops. Okay, so now that we've started and we have the arena rectangle, let's spawn some cheese. But before we can do that, let's just give ourselves a wee helper method, because I know we're going to need this later on. It's just a function which is going to give you a random position somewhere in those bounds. Random range. Yeah, and the rectangle gives you handy min-max values. Again, that's probably a nicer way to do this, but it works. So and this is exactly the same, but why? And let's give it, let's keep everything on the 0 plane. So back here, the arena is kind of pushed back, if we click on it, to 7 on the Z plane. So if we keep everything else in the 0, then that means it'll always be in front of the big blue square. So let's spawn some cheese. Game object instantiate. Cheese prefab. There, we have cheese. And position should be random position. Perfect. And we should also save a reference to the cheese. Perfect. And then we return success because it always succeeds creating cheese. So let's go back over here and see what happens. There we go, we start to get random cheese appearing. And if we look over here to the behavior tree, you can see that it's kind of lit up. So the green spawn cheese action succeeded, so that's why it's green. So it returned node val success, and then the sequence continued on to the wait action, and you can see when the wait action expires, it kind of flashes green, and that green gets returned back up to the sequence and it all starts over again. So you get this kind of live view of your behavior tree in action. If we were to click on some cheese, the lights go out, so it's whichever object you click on in the hierarchy view, it will show you what the current behavior tree state is. So quit that just now. We'd probably quite like actually to limit the amount of cheese that we can make, so public int max cheese. Let's default that to 2. Now the thing to notice here, there we go, it's just popped up, max cheese 2, that's probably enough cheese. Thing to notice here is that if you have ever used other behavior tree assets or libraries or development environments before, you normally have a blackboard, what's commonly termed the blackboard. So you would have your tree, you would have a blackboard that might be a little window full of values, and the nodes in your tree can interact with those values and update them and respond to them. But they are blackboard values, they're specific to the tree, and then you may have, depending on the environment, some plumbing to do to kind of wire those into other parts of your app and kind of extract the values out of your blackboard. in this system, there is no blackboard. The variables are your variables, just your regular variables. I added max cheese just as a normal property in a mono behavior. It appears in the inspector, and we can refer to it from within nodes in the tree. And it's as simple as that. And this extends to other components as well. So if there's another component, for example, over here, I can declare components which I want to become visible to my behavior tree. For example, maybe I've got a component which makes the cheese flash when a function is called. I can add the component into the tree, and then when I click on, say, one of these nodes, the method call, which is available through another component, will appear in here, and I can then call it from this component, which means that you're dealing entirely with common, normal, ordinary, everyday Unity concepts. Set regenerate code, make the button go green. Okay, so the next step, oh no, hang on, we haven't finished the maximum cheese thing yet, so let's just, well, first of all, let's give ourselves another little property. And if you're looking at this code thinking, my god, this is a mess, what's this guy doing? Yeah, it is a mess. I'm just trying to go as quickly as I can here. So, public, and we make it public just because it's nice to see these things pop up in the inspector. Probably could be private. Cheese count. There we go. Now, what have I done wrong? Oh, of course. So, if our cheese count is greater than or equal to our max cheeses, return fail. We can go back in here. We don't need to regenerate code, but I did it anyway. Hit play. 1 cheese, 2 cheeses, no more cheese. And if we click on the arena, there we go, spawn cheese is now failing. Right, so this is a bit boring so far, this game, so we need to add in some new characters, I think. So let's have a cat and a mouse, and let's make them sensible sizes. So let's move the cat over here, let's move the mouse just out of the way over there, and they're nice and they're in the same plane, which is good. Always good to check these things. And let's go into our scripts folder. I'm going to create 2 new behavior trees, one called cats, which we will drag onto our cat, and one called mouse. Which we will drag onto our mouse. There we go. So, we will ignore the cat for now, let's just focus on the mouse. So this is where it starts to get a little bit more interesting. We're going to use, there are 2 different, broadly speaking, there are 2 different types of decision making node. There are selectors, and there are sequences. So the selector will keep going until it finds a node which succeeds, at which point it has done its job and it doesn't proceed any further. A sequence will keep going until it hits something which fails, at which point it will stop. We're going to use a special kind of selector in this example, though. We're going to use a utility selector, which is kind of hard to describe, so I'm just going to go ahead and show what it does by using it. So if we click on utility selector, we get this utility editor popping up, which is asking us to add outcomes to the graph and all sorts of scary things like that. But all the utility node does is it evaluates some values in your character and works out which of the child nodes it has is the best one to choose in the current situation. So we are going to have a bunch of sequences underneath. So Control D just to duplicate that. We are going to have, we're going to have 4 basic actions. So this one, first one, let's call this flee from cat, because when the mouse is going to get too close to the cat, it's going to run away from him. The second one we are going to call get cheese, because when the mouse gets hungry, he's going to want to get some cheese. The next one, let's make this attack cat, because when he gets desperate, he's going to try and push the cat out of the way of the cheese. And the last one we're just going to call idle. When he doesn't want to actually do any of those things, he's just going to be idle, wandering around. And we can wire these up to the utility node, like so. Now the thing about utility nodes is you need to have a bunch of outcomes to match the children. So we're going to add 4 outcomes, which makes everything light up in interesting colours. So let's just describe these. Now each one has a need and a want, so you have to, it's quite difficult to actually come up with the correct terms normally, but you kind of have to express what each node represents in terms of what your character needs and how that translates into what your character wants. So this one is flee from cat is the first one, that's the yellow one. So what he needs is distance from the cat, and he wants to flee. So if he doesn't have the distance, he's going to run away. And the second one, get cheese, so what he needs is food, and what he wants is to feed. The next one is attacking the cat, so what he wants, or what he needs rather, is desperation. This is where it kind of gets a bit weird, because you don't need desperation, but the desperation in him is what is fueling his need to attack the cat. And if all else fails, or if he's completely satisfied, then if he needs nothing, he will do nothing, he will idle. So, what does all this mean? Let's start with the first one. This little graph here represents a distance from the cat and how much he will want to flee. So distance increases along this way, and I happen to know that this is around about 8 units in size, so we can say that the maximum distance is probably around about 8. So we can put in the input range of 0 to 8. And so the more of the distance, the less he's going to want to flee. So what we'll do is we'll edit this graph to be the other way around. In fact, we'll add in another key point here. Which is going to bottom out. So you can see by these numbers here that the graph kind of hits 0 around here. So anything above about 3.26 here, he's not going to want to flee at all. But the closer he gets to the cap below that range, his urge to flee is going to increase dramatically. So we can move on to the next one, which is how much he wants to feed. But actually before that, I'm going to just pop back into the mouse code here. And I'm going to add some properties. And we're going to say the food level, which is how much food is in his belly. We're going to say that's 50. So 0 to 100. So 100 would be a full belly. 0 would be an empty belly. 50 is where he starts off by default, which is stomach half full. So let's have a look. So the more food he has in his tummy, the less hungry he is. So let's do something similar. Something like this should do. So you can see we have a sort of nice gentler curve this time. So he's always going to be basically kind of wanting food. But the less food that he has in his belly, the more urgent that urge will become, and kind of until he is forced to go and find food and do something about it. Well, over here, which is what I haven't done for this one, but I will do in a moment, is wire up the input. So we said that the food level is from 0 to 100, so we'll put that in. And we'll say that it's a property. And you can see food level has already been selected there because it's the only one that we've created so far. So already we have the food level controlling this output. Over here, actually, we can have influences. So sort of other external influences that can affect this particular outcome. So influences are always ranged 0 to 1. So let's call this one gluttony. So let's wire up this influence level to gluttony, and you can test the influence here. You can see it's going the wrong way, so let's go. We want it to go to the right. So what the influence level does is it distorts the graph. So you can imagine this as the mouse's personality. So as we increase this property, the more likely he is to want to go and find food. So if you had multiple mice in this game, what were all running around, each one could have a slightly different personality, for example. Some want to find food more than others. Perhaps you can make it a negative influence so that the graph distorts the other way, so that your personality influence could be whatever the opposite of gluttony is. And you can edit the graph while it test values there as well, so you can see how it lies against all your other graphs. But let's just wire these ones up while we're here. So distance was to flee. So to wire this one up, we want to be able to work out how far away the mouse is from the cat. So let's add a wee method in here. And we will add a reference to the arena. And the arena we're going to treat as our kind of central point for logic. We're going to add a reference to the cat and to the mouse. Let's just wire that up before we forget. Arena gets the cat and the mouse. So, to get the distance from the cat, it's the position simple as that. So now we can wire this up. This time it is not a property, it's a method call. Distance from cat, 0 to 8. Done. So the desperation and attack one, we'll come back to that one actually. For the nothing idle one, we're going to link this one to food level as well, which is 0 to 100. And let's just say that the more food he has in his belly, the more satisfied he is, he's going to want to do nothing. But we're going to keep this one maxing out lower than the other ones just because it's more interesting when he does something. In fact, let's go back to the desperation one here. We'll just bring this one down just now. We'll come back to it later. Let's just make it nice and low to keep it out of the way. And regenerate code. Oh, and it's not letting me. So this is what happens when you've got a mistake in your tree. So I've got 4 sequences here, none of which have any child nodes, and you're not allowed to do that, so I'm getting errors down here. What I will do is add in some debug log nodes. All these do is print out debug log. Flee. Get cheese. Attack. Idle. We can wire them up. Regenerate code. And it's happy again. These debug log nodes, you can disable them at the tree level. So if we click over here in the tree object, we get the tree options for this mouse tree, or if we just click in the background, we also get it. So we can actually switch off all debug log nodes like that, and they won't have any effect. You can also disable the colouring and live update when it's running and things like that. You can override the namespace, the base class, things like that. And one thing that we will do right now actually is change the update type. So by default the update method of your mono behavior gets put into the generated part. Here it is here. which isn't always convenient because sometimes you want to update stuff yourself. So we're going to change this to manual, regenerate code, and now it becomes update AI, which means that you can now declare update in your own code and call update AI, which leaves you free to add your own code in to the update method. But let's make him actually do something. So let's start with the idle one, because that's the easiest one to kind of think about. You can move this over here, or you can hold down Control, kind of move groups of nodes around. So the idle node, let's keep the debug thing in here and also add in a selector. And what we're going to have is a property on the mouse, which is a target that it will walk towards. And when it reaches that target, it's just going to pick another target and walk towards that instead. So it's just going to basically choose a random position, walk towards it, and repeat over and over. So to do that, we're going to have, I'll build this up and then I'll explain it. So let's have a condition node. Okay, so I've just dumped a whole load of stuff onto the screen here. So let's try and explain what we're going to do. The selector, as we said before, is a node which will try each of its children in turn from left to right until it finds one that works. So what we've set up at first is, the first thing it should check is on the left, which is, have I already reached the target? If it is, let's choose another target. Otherwise, it will go into the next node, which is going to be moved towards the target. So let's give it a target first of all. And let's give it a method for choosing a new one. Choose new idle target. That will always succeed. So idle target is some random position in the arena. And we also want to be able to say actually, no, that's probably enough. So let's have a look. So this is the condition which you're going to check to see if we have reached the idle target. And I think I've actually used the wrong node. So we've got a custom condition, which is what I placed down. We've also got a distance check, which sounds much more appropriate. So we'll put that in, delete that one. We want to check the distance to some property, which is the idle target. And it's not always true. It's going to be true if it is less than, say, 0.1. So if you're very close to the idle target, it will trigger. And in that case, you want to choose a new target. So we will use a method call here. Now this isn't working. It says that no methods are the correct return type. Why is that? It's because I didn't save the file. Let's try that again. Straight away it jumps in. Choose new idle target. And once it has a target, it will move to the idle target. It's important to give your nodes names. That will become more important later on. So what we're actually going to do here is you'll see that these nodes have little green padlocks on them. And what happens with this little green padlock is that if a node returns running, you see here we for our method we just return success, but if we return running, then it would stay on that node until on the next frame, until it became success or fail or something else. So this tree would be locked into this position, and it wouldn't be able to assess anything else that happened down anywhere else in the tree. So if you imagine the cat comes along, stands right next to the mouse where it should be scaring it off, nothing will happen because the mouse is too busy moving to its target. So what we're going to do is we're going to change this to no latch, which means that on every frame we're going to start up here and we're going to go down here and we're going to move to this node, and every frame it's going to check, every frame it's going to go through and make sure it's doing the right thing. And if at any point it shouldn't be moving to the idle target, if it should be getting some cheese because it's suddenly become hungry, or if it's running away from the cat because the cat has appeared, then it will be interrupted and it will do something else instead. So we'll switch that latch off. There's a latch on this one, doesn't matter because it's just our simple method call, return success. It will make no difference what we set here. So we'll switch it off just to keep it looking the same. And we are moving it towards the idle target. And we will move quite slowly. Don't let speed down just because we want to see that the mouse is idling. It's not doing anything active like running around after cheese. It's just slowly meandering around. So hit regenerate. Let's see what happens. Right, so what's happened here is we're getting lots of null reference exceptions. That's because the reference to the arena was not set in the mouse. Let's hit play again. There we go, the mouse is now just wandering around while cheese spawns around him. And you can see we're getting lots and lots of debug messages telling us that we are idling. That's great. In fact, what I'm going to do is I'm going to switch off the debug logs because they're very annoying. So, we know how to idle. But we never get hungry. So the next thing we need to do is to get hungry. So now that we have control of our own update method, let's get hungry. So stick in a value here. So we're going to go down about 1.3 food units per second. So that will give us a kind of a fall off for our food level. So the food level, let's see, take away food burn per second, timed at delta time, and we will make sure it doesn't drop below 0. So our little mouse will get hungrier and hungrier over time. Actually, one thing we could do, let's have a visible readout here. So let's create a canvas. And onto the canvas, let's put some text. Let's put this down here where we can see it. Let's move that over there. And this could be the food level. We will make this black so we can see it properly. Let's add a reference to it to the mouse. So food level readout. We'll add more readouts later on, so let's have a function for it. Nice and simple. Switch this off, go back to, there we go. Now if we run it, nothing happens because we forgot to set up the references again. Food level, there we go, so he's getting hungrier and hungrier until eventually he's going to want to do something about it. You can see he's actually stopped here, so if we pause this, go back in here, he is already hungry enough to get the cheese. So that's why he's stopped idling. He's become hungry and he wants to eat. So let's do something about that. Let's try and show him what to do. Right, so if we want to get the cheese, we want to check to make sure there is actually some cheese available. So first things first, let's stick in a wee condition. And let's call this condition is cheese available? Oops. Cheese count greater than 0. So if there's cheese on the screen, this will return true. So it's a simple Boolean function, nothing magic about it. And if we come back in here, you can see that it's a method call, is cheese available. Wire that up to the sequence. After that we want to have a wee selector. So if this is not available, it won't reach this selector, it will just come back and say fail. Because what we want to happen, if we click on this utility node up here, over here we have this fallback behavior, and it has two different options. So if we say fail, what will happen is this will say there's no cheese available, there's nothing in the screen. This will return back to fail, this will go up to fail to the utility node, and it will stop. And then in the next frame it will come in, say I'm hungry, get the cheese, is cheese available? Nope, fail, fail, and it'll stop. And the mouse will just stand there. But we don't want it to just stand there, we want them to do something else. So this utility node, which is ranking these four options from best to worst at any given moment, we would like it to move on to the next best thing if there's no cheese available. So we'll go to next best, no cheese will be available. I'll go back, it will say, okay, well, which of the other three is the best thing? And it might decide that idling or attacking the cat would be the best thing to do if there's no cheese around to satisfy the most pressing need, which is hunger. There is cheese available. If the cheese is right next to us, we want to eat it. So we'll have a little sequence for that. Eat cheese. If there is not, we want to move to the nearest cheese. So we'll have a move node. Move to the cheese. And before we forget, let's switch the latch off. So how do we eat cheese? We need another condition. Distance check, which is going to be, is cheese very close? So that's going to get the closest cheese, work out if it's very close, and if it is close, do a custom action which will be eat cheese. And this will be moved towards cheese. So you can kind of see a pattern here. We're basically building up the behaviors that we want, and we're adding in simple properties to support that, asking simple questions about the scene and what is available, what information is available to us. So first of all, let's work out what the closest available cheese is. So we'll add that into the arena, because the arena knows all about cheese. Get closest cheese. So first of all, a quick rejection. If there's no cheese there, just return null. Okay, so get closest cheese to what? To some position, which would be the position of the mouse. And we want to loop over the cheese, so let's do a simple search. So we're going to search through each index in the cheese list and comparing the distance to that cheese to the best one we've found so far, and making a note of it. And we'll probably have to increase our index that we're looking at in the loop. Again, scrappy code, very sorry. We only need to get the square magnitude because we're doing comparisons. We don't actually care what the distance is, only which is the best. If this distance is better than the one we've got so far, then record it. And once we've come out the other side of this loop, we will have the closest cheese. Right, so back into the mouse, distance to closest cheese. closest cheese, closest to our position. There's no cheese. Return some massive value. Otherwise, return the distance. There's a bit of repetition here, but it's for this example, it's absolutely fine. Perfect. Now we can go back in here. Actually, no, we can't. So let's get let's just copy this in here because it's doing roughly the same thing. Turn okay, so we can now get the closest cheese position and the distance to the closest cheese. So, is the cheese very close? Let's see. It was a method call, wasn't it? Closest cheese position. If it is less than 0.1 to the closest cheese, then yes, the cheese is very close. So we will eat the cheese. Let's just go back in here where we're doing it. Public val eat closest cheese. And what we're going to do here is get the closest cheese. We're going to say arena eat cheese. Generate method. And we remove that from our list of cheeses. And also destroy it. Should remove it from the scene. And also, because you've eaten some cheese, cheese food value, let's say 10. So our food level goes up by cheese food value, and let's cap it at 100. So we can't go above 100. Back in here. Oh, I'm getting some warnings here. This is the random thing. It needs it's interfering because I've got a system included up here. So Unity engine. Just do it disambiguous it. Disambiguous? Is that a word? I don't know. Disambiguize. There you go. It's a better word. So is the cheese very close? We've done that one. Eat the cheese. Eat closest cheese. Done. No latch is required. Switch it off anyway. Move towards the cheese. Want to move towards not the idle target this time, but the result of a method call, which is closest cheese position. and we're going to move towards the cheese a bit faster than the idle speed. Just make it say 1.2, just so that we know that the mouse is doing something. So we may actually be able to see this work now. So if we hit play, you can see down here there's the food level. He's getting hungry. He actually ate the cheese. There we go. So he is idling just now. He's no idea what he's doing now. So let's have a look. Behaviour. Click on the mouse. He's trying to run away from the cat. That's what's happening. So he's getting close to the cat. The cat is, this behaviour is undefined because we haven't done it yet. And he's just getting in knickers and a twist. So we need to complete this. This should be very simple. All we have to do is put in a move away from the cat. So, did we have the cat position? No, we didn't. So we'll add in the cat position. To the mouse. If I can spell. Cat position. And we're going to run away from the cat. Yep, already selected. This checkbox down here says away from. Now, in this current state, this isn't going to be very good because we have a latch on here. It says latch until complete. It's moving away from the cat. It will move away from the cat forever and ever because it will never be complete. You can never be sufficiently away from the cat. So what we have to do is we have to put a cap on this to stop it moving on forever. So we're going to say complete after timeout. If this was moved towards the cat, then it would reach the cat and it would stop. And then it would move on to the next node. If we said latch complete after timeout and we set a timeout that was longer than the time it needs to get to the cat, then either reaching the cat or the timeout would end the node successfully. But we are moving away from the cat, so it will always complete after this time. So we're just going to make him run away from the cat at 2 units per second for points, I don't know, 0.4 in a second. Let's try it. Hit play. It's going for the cheese. And we're going to have to cheat here, so oh no, he might actually reach the cat all by himself. There we go, run away from the cat. Now he's going for the cheese. So he didn't run away from the cat very far, so let's just dash away from cat. Let's increase the timeout, so let's say 0.6, so he runs away a wee bit further. Perfect. Now, attacking the cat. I've just realised that I've been making this video zoomed out. Hopefully you can see this okay, but if I zoom in, this is the normal scale. You can zoom out quite far just to help you navigate around and zoom back in. So let's just move these nodes out of the way for now. And let's just concentrate on attacking the cat. So this is a little belligerent mouse who, when desperate, and by desperate we mean there's a cat close by and he's very hungry, he will attack the cat. So we're going to put in an actual sequence, a kind of animated sequence of events that the mouse is going to do. He's going to rush at the cat, he's going to whack it, and then he's going to retreat and run away again to safety. So let's just block this out a bit. He's going to rush towards the cat. And actually we can fill this out just now because we've already got the cat position. Going to rush at the cat at 4 units per second, like some kind of maniac. And once he is, let's see, we're going to use another option here. Let's say complete after condition. But first of all, let's create a condition. So we're going to create a condition that tests to see how far away the cat is and whether it's within striking distance. So distance from cat. Actually, wait a minute, let's change this again. So cat within distance. So what we have here is this a method? There we go. Simple boolean, we pass in a distance, and if the cat is within that distance, it will return true. If we go back into here, we can say complete after condition. This is the condition section here, opens up. We want it to be a method call. I want to say that it's cat within distance. And what happens is you get a little box that pops up and tells you the parameters to that method that the tree will pass in, the behavior tree will pass in. So we'll hit in 0.3. So if what this node will now do is the mouse will rush towards the cat and continually checking to see whether the cat is within 0.3 units of distance. If it is, the node will complete successfully. Next up, we want to do some kind of attacking animation. So let's just set one up. We have another sprite in here that goes pow. Add that to the mouse. That's a bit too much pow. Shrink that down. Move it over here. In fact, let's bring it in front. There. So we can just set up a quick animation. Assets, animations. Mouse still. Create a new clip. Mouse bow. So when the mouse is still, we don't want the pow to be active. When the mouse goes pow, we do want the pow to be active. We want this to be about 45 frames, that's good. And we'll jiggle it about a bit. So do a really simple, quick animation. back into the animator for the mouse. So the mouse is still as the default. Then it can go pow, then go back again. So we've got our exit time, and I don't want any fancy blending, I just want to cut between the animations. So this one will need a trigger, and let's call the trigger bow. So it goes bow, and we get a nice animation. So we want to wire this up to the behavior tree. We also want to attack the cat at the same time. So what we're going to do is we're going to add in another sequencer, the parallel sequencer. So what this does is not so much sequencing as doing things all at the same time. So we've got a custom action, which will go hit cat, and this will call a function which will do whatever we need to do to tell the cat that it has been hit. We will play our animation. So by default it's set up as a trigger. We just need to give it the trigger name, which is pow. The parallel node, you'll see it also has a green lock on here. It says latch until complete, but we need to know what complete means for a parallel node. In our case it doesn't matter very much because these will both complete immediately, but you can set it to either all must succeed or any must succeed. So if this node took more than one frame, took several seconds to complete, but this one happened instantly and it was set to any must succeed, then the parallel node would complete instantly, because as soon as any one of its children is complete, it finishes. But all must succeed means the parallel node will wait for all of its children to become successful before continuing. The animation, I set it to 45 frames, which is 0.75 seconds. So we'll add in a parallel wait as well, so that we wait for the animation to play out. We then need to, what we'll do is we'll run away, we'll stick this in the parallel node so that it all happens at once, but we will also call the choose new idle target method to choose where to run away to, and then we will rush to that idle target. We can call that retreat. So also at 4 units per second. So let's see what that looks like. You know what, I've just realised it's never going to attack the cat, because we didn't set up the utility node correctly for it, did we? So what we can do actually is, we had this gluttony value in here which we've still to play with. Let's call this one belligerent. This is for testing, so we can make the mouse more belligerent and more likely to attack the cat. We want to attack the cat when we are desperate. So let's try and figure out what a measure of desperation might be. So we're going to make up a value, which we're going to call desperation, I'm going to say that this is based upon food level somehow, and the distance from the cat. So the cat's pretty close, there's no food around, he's very hungry, he's going to be more desperate. So okay, so what we're doing here is we're dividing the distance from the cat by 8 because we know that the board is roughly 8 units in size, to bring it down to roughly the 0 to 1 range, and we're inverting that, so that by doing 1 minus, so that the closer he is to the cat, the more desperate he will be. Excuse me. And then let's factor in the food level as well. So add those values together. So we've done the same thing to the food level. So the more hungry he is, the higher this number will be, and it will be roughly in the 0 to 1 range. Add them together and we get a desperation value which is roughly in the 0 to 2 range. So if we go back to the utility graphs, let's bring this down a bit. So we now have a property called desperation from 0 to 2. We have a value for belligerence, and we want to plot this graph with a higher urge to attack the more desperate he is. So let's do that. This must be negative. So the more desperate he is, the more his urge to attack the cat suddenly rises. And his desperation is, we've made it a kind of mashup of how hungry he is and how close the cat is to him. And we've also set up this belligerence influence value, so that the more belligerent personality our mouse has, the more likely he is to want to just go and attack the cat. So let's pump this right up to no, hang on. Let's go over to the mouse. See, what I was doing there was I was turning up the test influence. This means nothing. All it does is show you the shape of the graph. So if we want to actually change the belligerence, we have to go over to the mouse and change its actual belligerent value up to 1. So he's a very angry mouse and very keen for a fight. So that we can see what happens. Well, it seems to be working, except we're not seeing any POW animation. So let's have a look and see if we can see what's going on. Let's just see if the animation is working. So yeah, we see the triggers being triggered. Oh, I know what I've done. I didn't actually set up the condition, did I? So there, we set up the condition on the animation. POW. Just going to keep attacking that cat. And the one thing we didn't do is the hit cat method. So let's do that. and we'll work out what that actually means in a moment. So that's pretty much it for the mouse, but it doesn't mean very much because the cat is just standing there being boring. So let's have a look at the cat. Now, before I get into the cat, let's just add one more wee animation. So we've got a cat here with us. This is our cat script. Our cat script is attached to our cat. Let's give him a bit of personality. So let's go for a meow script as well. Let's drag this one to our cat. So the cat now is a cat and a meow. And in the meow, we've got another little sprite in here. It says meow. Like that. And we'll very quickly just create a reanimation. Cat, not meow. Oh dear, done that wrong. Let's remove this. Create an animation, let's delete this one. Cat, not meow. On the cat for a change, I've created it on the wrong object there. So let's create it on the cat so that we can refer to the meow. Delete, not active. Clip, cat, meow. I don't think that's how you spell meow, but I've started, so I'll finish. Let's make this 45 frames as well. Let's change its position. Over time. And let's create an animator. Cat, cat not meow, cat meow. So we need a trigger, don't we? Let's remember to set up the trigger this time. There we go. No exit time, no transition, just meow. And when it's meowing, we have an exit time, which play the whole damn thing, and we don't want any transition. Thank you. So we can actually switch these off so they're disabled by default. And then here we're going to have a sequence. We're going to wait. I'm going to play the animation. So you've got the legacy API as well. So you can do play, blends, and crossfades, and you can do the same with the Mechanim API. But we're just going to trigger animations, and we're going to wait a random value between 1 and 10 seconds. So why did I do that? Well, the reason I did that is to show that you can have more than one behavior tree attached to the one object. So if we now play this, We'll see that the cat's definitely not. Oh, there we go. He's saying meow at random intervals. He is also being governed by the cat script, which isn't actually doing anything, but it is attached to him, and it will do stuff once we've created it. So if you imagine a more real-world example, you might have multiple behavior trees attached to your character. One might be working out the navigation of the character, what to do, controlling his legs. You might have another behavior tree just controlling his head, controlling what your character is looking at, perhaps even triggering descriptions of what he's seeing to make him feel a bit more alive. And these things are all happening completely independently of each other. As long as you don't have two behavior trees both trying to control his legs in different ways, then you're not going to become unstuck. But you can split up your trees across your character like that. They don't have to be one tree that does everything. Okay, so what is the cat actually going to do? Well, he's going to wander around idling like the mouse does, just sort of picking a random target, wandering to it, wandering to the next target, and occasionally he's going to get hit by a mouse. So let's do the idle part first. So that's going to be a sequence. That's not a sequence. And it's going to be a sequence where we choose a target and wander to it. So let's choose a target and let's move. And we are going to go back to the cat, and we're going to borrow some stuff from the mouse here. Idle target, we need the arena, we need to choose a new idle target, but let's fix our imports. Let's call this wander target just to differentiate it. So we choose new wander target. So he's not idling, he's wandering, because he's a cat. So back in here, we are going to wander, choose a target, and we're going to move towards it. And we're going to do that slowly. We generate code, hit play, and it's not working. So what have we done wrong? One of the problems that we have with multiple behavior trees being attached is that it will show you only one of them in the live view, because it can't tell when you click on cat when the application is running whether you want to see the meow behavior or the cat behavior. So for now I'm going to remove the meow behavior. We'll reattach it later. We're going to hit play just so that I can see what's going on. I see what's going on. We've got sort of no reference exceptions because the arena was not linked. So let's try that again. There we go. Our mouse is still set on highly belligerent. Once the cat gets to wherever he's going very far. Yep, he chooses another target and wanders that way instead. So let's, first of all, let's go to the mouse and stop him being so violent. And let's go back to the cat and tell him that he has been hit. we need a way of telling the cat that he has been hit. To do this, we're going to borrow an idea from Mechanim, and we're going to set up a trigger. So private bool is hit. So the trigger, when it is a value which is set to true, and will be cleared back to false when it is checked. So you check it once and it automatically resets to false. So let's do that. Create a property. So if you check the isHit property and you have been hit, it will be reset automatically back to false, and the value will be only usable once. And we should also have a way of setting it. So no, actually we don't do that. We just need to do. Whoa! Thank you, IntelliSense. Right, so the mouse, if we remember, we had a hit cat method. Which now does something. So when the mouse hits the cat, it tells the cat that it has been hit, and we set this boolean flag in here. So let's add in a selector over here. And on the left, we'll have another sequence for when it is hit. So we'll have a condition first of all. Is hit. Now you can see that the actual private property is showing up there as well. You do have access to private properties through node values, but we're going to use the isHit property here because we wanted to clear the value. Now we have a bit of a problem here, because if it is not hit, it will return back up here. It will go down this sequence, it will choose a new one to target, it will move to the one to target, and this little green padlock here says that it's going to latch into this node and stay wandering, which means that if the mouse hits the cat while it is wandering, which is pretty much all of the time, it will not react, because it will not suddenly leap over here and do all the hit stuff that we're about to build. So we want to be able to interrupt this. So what we're going to do is we're going to choose the reset to node after condition option. And we're going to choose selector. So what these are, remember I said that it's important to name your nodes, so let's name this one root node move sequence. So if that's a bit clearer, it's these two nodes here. You can reset back to a node that you've come through, sort of above in the hierarchy, based on some conditions. So if while you're wondering this condition suddenly becomes true, I want to move back to the root node, like that. I could also use the reset tree after condition, which will do the same thing. Now reset tree just goes back to the start node and begins again, which is effectively the same thing in our particular situation. And what will happen is we're going to check, is it hit? Yes. So we'll reset back to the root node. It will start again down this branch. Are you hit? And it'll do all the hit stuff. But big problem, our hit condition is going to be cleared by this test over here. When we come down here, it's not going to be true anymore. So we need to account for that. Let's change is hit into a method. Where clearing is optional. And then we can change this source to is hit, the method. We don't want to clear it here. We do want to clear it over here. Because this is where we're actually dealing with the hit. And what are we going to do to deal with it? We're going to set up another animation sequence and the cat is going to recoil away from the mouse. And the recoil is simply going to move away from the mouse. Have any method calls. Let's add a mouse position property to the cat. Let's make it a method, just because. So same idea as before. When we did this with the mouse, we've got method call, we've got the mouse position, moving away from it, and we want a timeout, quite a small timeout. Just so that it jumps back a little bit, and it's moving quite quickly. So you can also use tween values here. So we can, let's do an ease out. See, this is the, right, so the latch timeout we've got 0.1 seconds, so we want to match that with the duration of the tween. No, we can't use the tween, because we need to do away from. You can't move away from with a tween, because away from has no end. So let's just leave this. If we're moving towards something, fine. There's all sorts of tween options that you can use, including, I believe, I think in the rotation node there's a seeking tween, where you can tween towards a changing target. Kind of hard to explain. But we're not doing that right now, so let's just recoil, so he moves away from the mouse, and we also want to trigger an animation. Let's add another little animation to this cat. So let's add another layer separate to the meow, where he is stunned. Let's not, because this is not the cat. This is the cat. stunned. And again, just for easy calculations, 45 frames. And he is going to shake about, all stunned, wondering why this is happening to him. Perfect. And we have to add this back into the layer here. Oh dear, I've saved it into the wrong folder, haven't I? There it is. And let's have a little trigger. Stun. Don't want any durations. Okay, so let me see, what am I doing here? So, right, cat stunned. Once it is complete, I seem to be making a mess of this. Has an exit time, no duration. Let's just clear this out of the way. So he's stunned. Exit time. Nope. Transition 0. That should do it. Let's just test that. So stun him again. It's meow. The meow seems not to be working at the moment. I think I have messed up the layers. I think it's because I have a cat not meow here and a cat not meow there. Possibly, maybe. But I'm not going to be bothered about it right now. Let's just forget the meow. Concentrate on having a stunned cat. So we're going to need a animation trigger for stun. Unlike the move, which has the timeout on it, this has no timeout, so we can need to fake it with a parallel node. There. And a wait. Because we know the animation is 45 frames, 0.75 seconds. And the parallel node is locked to wait for everything to complete. Once he has recoiled, the tree will reset and he'll do whatever he was doing before. So let's go back to the mouse, pump up his belligerence again, hit play, there we go. Now down here, let's just make this bigger. The cat is now being attacked by this crazy little mouse. Let's wind down his belligerence. Mouse is idle. He's going for the cheese. He's running away from the cat. He's getting more and more hungry. He's going to be pushed into a corner here, literally. And eventually he's going to become so desperate, he's going to attack the cat. Nope, he's got past the cat. And he's gone for the cheese. Bumping up his food levels. So we've gone from a belligerent mouse rather, to a mouse who will not attack this cat under any circumstances. Come on, you can do it. He's too afraid of this cat, come on. So what we probably need to do is go back into the mouse and tweak these levels a bit. Maybe we need to bring this back a bit. Add another key in here. More likely to attack the cat. But we know that it works because when we increased the belligerence levels, he attacked all the time. Let's just see what happens here. But what we have created is quite a complex set of steps. Pause. But if we hit play again here, have a little look. There we go, he's attacking the cat straight away. Now he's going for the cheese. His food level goes up. Food level is going up quite high. He's just idling now. Now he's going for the cheese. Idling again, he's not hungry. He's going to go for this cheese, but he's going to be pushed away by the cat. Oh, no, he's going to attack the cat. So you can see we can control this stuff quite, we can kind of tune our characters' behaviours to quite a fine degree. I mean, this is quite a contrived example, but you can imagine a more real-world example with different, more realistic outcomes. For example, do I go for the ammo? Is my ammo low? Is my health low? Do I need to find a medical kit? Which objects do I need to find? Am I under attack? That's a kind of higher priority. I should find some cover. Those kind of decisions could be rolled up in this kind of utility graph, or even just a simple behavior tree with simple inputs and outputs, binary decisions. This asset is probably a couple of months away from release. It's basically functionally complete. There's still a couple of little rough edges that need rounded off. If you are at all interested in trying it out, then I'm actively looking for beta testers to try this build. There will probably be a beta 2 release as well, with some extra functionality. Drop me a line, check out the web address and the video description to find out how to get in contact, and let me know what you'd like to do with it. That would be great to know. If this looks useful to you, what you're going to use it for, let me know, and I can get this thing tested and released. Thanks for watching.